Have you ever wondered how a single mind could illuminate the entire world and transform human civilization forever? Picture this: a young boy with only 3 months of formal education would grow up to hold over 1,000 patents and create inventions that still power our daily lives more than a century later. This is the extraordinary story of Thomas Alva Edison, the man who didn't just invent the light bulb, but engineered the very foundation of our modern electric world. Most people think they know Edison's story. They've heard about the light bulb, maybe the phonograph, and that famous quote about genius being 1% inspiration and 99% perspiration. But what if I told you that everything you think you know about Edison barely scratches the surface of one of history's most complex and controversial figures? What if the real story is far more fascinating, darker, and more human than the sanitized version we learned in school? In this complete exploration of Edison's life, we're going to uncover the truth behind the legend. We'll discover how a partially deaf boy from Ohio became the most prolific inventor in American history. We'll explore the fierce battles he fought in the War of the Currents that literally electrified the nation. We'll examine the empire he built at Menlo Park, the world's first industrial research laboratory, and we'll confront the uncomfortable truths about his business practices, his treatment of competitors like Nikola Tesla, and the methods he used to destroy anyone who stood in his way. This isn't just a biography. This is the story of how one man's relentless pursuit of innovation shaped the world we inhabit today. From the first recorded sound to the birth of the movie industry, from electric power systems to the modern corporation itself, Edison's fingerprints are everywhere. But genius comes with a price, and Edison's story is as much about what he destroyed as what he created. So settle in as we journey through the complete life of Thomas Edison, from his humble beginnings in Milan, Ohio, to his final breath in West Orange, New Jersey. This is a story of triumph and failure, innovation and exploitation, brilliance and ruthlessness. By the end, you'll understand not just how Edison changed the world, but how the world changed Edison, and why his legacy remains both celebrated and deeply complicated to this day. Thomas Alva Edison entered the world on February 11th, 1847, in the small canal town of Milan, Ohio. His arrival came at a time when America was rapidly transforming from an agricultural society into an industrial powerhouse. The railroads were expanding, telegraph lines were connecting distant cities, and inventors across the nation were racing to create technologies that would define the future. Into this world of possibility and change came a child who would exceed everyone's wildest expectations. Edison's father, Samuel Edison Jr., was a lighthouse keeper and carpenter who had fled Canada after participating in an unsuccessful rebellion against British rule. His mother, Nancy Matthews Elliott Edison, was a former schoolteacher from a well-educated family. The combination of Samuel's practical mechanical skills and Nancy's intellectual curiosity would prove crucial in shaping their son's unique approach to invention and learning. From his earliest days, young Thomas displayed an insatiable curiosity that both delighted and exasperated his parents. He asked endless questions about everything he encountered, often following up with his own experiments to test the answers he received. When he was told that birds could fly because they ate worms, 6-year-old Thomas fed a mixture of worms and water to a friend, hoping to give her the power of flight. The experiment ended with a sick child and an angry mother, but it demonstrated the scientific method that would guide Edison throughout his life. Form a hypothesis, test it, and learn from the results, regardless of whether they matched expectations. The Edison family's fortunes took a dramatic turn when Thomas was 7 years old. The completion of the Lakeshore Railroad bypassed Milan entirely, transforming the once thriving canal town into a backwater almost overnight. Samuel Edison watched his business prospects evaporate as commerce shifted to the new railroad routes. Like thousands of other American families during this period of rapid change, the Edisons packed their belongings and headed west in search of new opportunities. They settled in Port Huron, Michigan, a growing lumber town on the shores of Lake Huron. Here, Samuel found work in the lumber business, while Nancy focused on raising their children. The move would prove fortuitous for young Thomas, as Port Huron's location made it a natural stopping point for ships and trains, exposing him to the latest technologies and innovations passing through the rapidly expanding transportation networks. Thomas's formal education began in Port Huron, but it would be brief and troubled. His teacher, Reverend George Engel, ran a strict classroom where students were expected to memorize lessons and recite them back without question. This approach clashed completely with Thomas's naturally inquisitive mind. While other children dutifully repeated their lessons, Thomas asked why things worked the way they did, often challenging the explanations he received. The situation came to a head when Reverend Engel, frustrated by Thomas's constant questions and apparent inability to focus on rote learning, declared the boy addled and suggested he might be mentally deficient. When Nancy Edison heard about this assessment, she was furious. She marched into the school, confronted the teacher, and withdrew her son from a formal education forever. Thomas Edison had received exactly 3 months of traditional schooling, a fact that would later become part of his legend as a self-made genius who succeeded without formal credentials. Nancy Edison took charge of her son's education with remarkable results. As a former teacher, she understood that different children learned in different ways. Instead of forcing Thomas to memorize facts, she encouraged him to explore subjects that interested him. She introduced him to books that fired his imagination, including Isaac Newton's Principia Mathematica and Richard Green Parker's Natural and Experimental Philosophy. The Parker book proved particularly influential as it contained detailed descriptions of scientific experiments that readers could perform at home. Thomas threw himself into these experiments with enthusiasm, transforming the family basement into a makeshift laboratory. Nancy supported these pursuits, even when they resulted in explosions, strange smells, and occasional disasters. She recognized that her son was learning more from his hands-on experiments than he ever would from a conventional classroom. By age 10, Thomas had read advanced works on chemistry, physics, and natural philosophy. He had also begun to develop the methodical approach to experimentation that would characterize his later work. He kept detailed notes of his experiments, carefully documenting what worked, what failed, and what might be tried next. This systematic approach to learning and discovery would become the foundation of his revolutionary approach to invention. The Edison family's financial situation remained precarious throughout Thomas's childhood. Samuel's income from the lumber business was irregular, and the family often struggled to make ends meet. This economic uncertainty taught young Thomas valuable lessons about the relationship between innovation and commerce. He began to understand that inventions, no matter how clever, were worthless unless they served a practical purpose and could be profitably manufactured and sold. When Thomas was 12 years old, the Grand Trunk Railroad reached Port Huron, connecting the town to Detroit and the wider world. This development would change the course of his life in ways no one could have predicted. The railroad brought not just transportation, but also opportunities for enterprising young people willing to work hard and think creatively about serving the needs of travelers. Thomas convinced his parents to let him work on the railroad, selling newspapers and snacks to passengers during the daily run between Port Huron and Detroit. This job gave him his first taste of business and showed him how to identify customer needs and satisfy them profitably. He soon expanded beyond simple sales, creating his own newspaper called the Grand Trunk Herald, which he printed on the train using a small press he had acquired. The newspaper venture demonstrated several qualities that would define Edison's later career: his ability to spot opportunities others missed, His willingness to work incredibly long hours to achieve his goals, and his talent for combining technical innovation with business acumen. The Grand Trunk Herald was profitable because Edison understood something that established publishers had overlooked. Train passengers wanted news that was specifically relevant to their journey and their destinations. Edison's entrepreneurial spirit extended beyond the newspaper. He established a complex business network that included selling produce from his mother's garden to passengers and hotel owners in Detroit, and even setting up a small chemistry laboratory in the train's baggage car where he continued his scientific experiments during the long daily runs. This period of Edison's life came to an abrupt end when one of his chemistry experiments went wrong, causing a fire in the baggage car. The conductor was furious and threw both Edison and his equipment off the train at the next station. Legend has it that the conductor also boxed Edison's ears so hard that it contributed to the hearing loss that would plague him for the rest of his life. Whether this story is entirely accurate remains debatable, but there's no question that Edison's hearing problems began during his teenage years and would profoundly affect both his personal life and his approach to invention. Rather than viewing his partial deafness as a disability, Edison would later claim it was actually an advantage, allowing him to concentrate more intensely on his work by filtering out distracting sounds. The end of his railroad career forced Edison to consider new directions for his energy and talents. He had tasted both business success and scientific discovery, and he was hungry for more of both. The question was how to combine his growing technical knowledge with his proven ability to identify and satisfy market needs. The answer would come through his introduction to the telegraph, the revolutionary communication technology that was transforming American business and society. At age 15, Edison learned that the local telegraph operator in Port Huron was leaving for a better position elsewhere. The job would become available, but it required someone with knowledge of both the technical aspects of telegraph operation and the business skills necessary to manage the office efficiently. Edison saw this as the perfect opportunity to combine his interests in technology and commerce while earning a steady income to help support his family. He convinced the station agent at Mount Clemens to teach him telegraphy in exchange for saving the man's 3-year-old son from an oncoming train. Whether this dramatic rescue actually occurred or was embellished over time, Edison certainly did learn telegraphy from the Mount Clemens operator, and his skill with the telegraph key opened up a new world of possibilities. The telegraph was the internet of the 19th century, instantly connecting distant cities and enabling the rapid transmission of news, business information, and personal messages across vast distances. Telegraph operators were the gatekeepers of this information flow, and skilled operators could find work in any city or town with telegraph service. For a young man with Edison's restless energy and desire to see the world, telegraphy offered both steady employment and the opportunity to travel throughout the rapidly expanding American frontier. Edison's years as a traveling telegraph operator from 1863 to 1868 would prove crucial to his development as an inventor and entrepreneur. During this period, he worked in cities throughout the Midwest and South, including Indianapolis, Cincinnati, Memphis, and Louisville. Each position exposed him to different aspects of the telegraph industry and helped him understand both the technology's capabilities and its limitations. More importantly, his work with telegraph equipment gave Edison hands-on experience with the cutting-edge technology of his era. He learned to repair and modify telegraph instruments, and he began to identify ways that existing equipment could be improved. His first serious inventions grew directly out of his work as a telegraph operator, as he sought to solve practical problems he encountered in his daily work. Edison's reputation as a skilled operator grew during his wandering years, but so did his reputation as something of an eccentric. While other operators were content to simply transmit and receive messages, Edison was constantly tinkering with the equipment, trying to understand how it worked and how it could work better. His supervisors often found him with telegraph instruments disassembled on his desk, components spread across the office as he tested theories about electrical circuits and signal transmission. This compulsive need to experiment sometimes got Edison into trouble with his employers. In Cincinnati, he was fired after modifying the office's main telegraph line without permission. In Memphis, he nearly electrocuted himself while attempting to improve the power supply system. But each failure taught him valuable lessons about electricity, magnetism, and mechanical engineering that couldn't be learned from any textbook. During his time in Louisville, Edison made his first serious attempt at invention. He had noticed that the automatic repeater systems used to relay messages between distant cities often garbled signals, causing costly delays and errors. Working late into the night after his regular shift ended, Edison designed an improved automatic repeater that could handle multiple messages simultaneously without signal degradation. The device worked brilliantly in his tests, but when Edison tried to demonstrate it to his supervisor, the man showed little interest. Telegraph companies, Edison learned, were often reluctant to adopt new technologies unless they promised immediate and obvious cost savings. Innovation for its own sake meant nothing to businessmen who had invested heavily in existing systems and were wary of expensive changes. This experience taught Edison a crucial lesson that would guide his entire career. Technical brilliance alone was insufficient for commercial success. An invention had to solve a real problem that customers were willing to pay to fix, and it had to be economically viable to manufacture and maintain. This understanding of the relationship between innovation and market forces would become one of Edison's greatest strengths as an inventor-entrepreneur. Edison's hearing continued to deteriorate during his telegraph years, a problem that created both challenges and unexpected advantages. On the negative side, his deafness made it difficult for him to hear faint telegraph signals, especially in noisy environments. He compensated by developing an unusually sensitive touch for the telegraph key, learning to read messages through the subtle vibrations transmitted through the equipment rather than relying on audible clicks. But Edison discovered that his hearing loss also provided benefits that fully hearing operators didn't enjoy. He could concentrate intensely on complex problems without being distracted by conversations, street noise, or other audio interruptions. This ability to focus completely on technical challenges would become one of his defining characteristics as an inventor. By 1868, Edison had decided that his future lay not in operating telegraph equipment, but in improving it. At age 21, he resigned from his position as night operator in Boston and committed himself entirely to invention. He had saved enough money to rent a small workshop and purchase basic tools and materials. More importantly, he had identified several significant problems with existing telegraph technology that he believed he could solve. Boston in the late 1860s was an ideal place for an aspiring inventor to establish himself. The city was home to numerous manufacturing companies, financial institutions, and technical schools that could provide both customers for new inventions and sources of capital for development. The intellectual atmosphere was stimulating, with lectures, demonstrations, and discussions about the latest scientific discoveries happening regularly throughout the city. Edison's first patented invention was an electrical vote recorder designed to speed up the process of legislative voting. The device allowed lawmakers to register their votes by flipping switches at their desks, with the results automatically tabulated and displayed. Edison was convinced that politicians would embrace any technology that made their work more efficient. He was wrong. When Edison demonstrated the vote recorder to a committee of the Massachusetts legislature, the politicians were politely uninterested. They explained that the slow, traditional voting process wasn't a bug, but a feature. The time required for manual vote counting provided opportunities for last-minute negotiations, coalition building, and compromise. Speeding up the process would actually make their jobs more difficult, not easier. The failure of the vote recorder taught Edison another invaluable lesson about innovation. Just because something could be improved didn't mean it should be improved. Successful inventions had to align with human behavior and institutional needs, not fight against them. From that point forward, Edison would never work on an invention unless he had first identified a clear market demand for it. Despite this setback, Edison's reputation as a skilled electrical inventor began to attract attention from Boston's business community. Telegraph companies were facing increasing pressure to handle growing message volumes more efficiently, and they were willing to pay for innovations that could increase their capacity and reliability. Edison's breakthrough came with his development of an improved stock ticker, a specialized telegraph device that transmitted financial information to brokers and investors throughout the city. Existing stock tickers were notoriously unreliable, often breaking down during busy trading periods when accurate information was most crucial. Edison's redesigned ticker was more robust and could handle much higher message volumes without mechanical failure. The success of his stock ticker brought Edison his first significant financial return from invention. More importantly, it demonstrated that he could combine technical innovation with business success. Word of his achievements spread quickly through the tight-knit community of telegraph inventors and entrepreneurs, establishing Edison as a rising star in the field. But Boston, for all its intellectual stimulation, was ultimately too small for Edison's growing ambitions. The real money in telegraphy was in New York, where the major companies had their headquarters and where the largest investments in new technology were being made. In 1869, at age 22, Edison made the decision that would transform his career. He moved to New York City with almost no money, a head full of ideas, and an unshakable belief in his ability to revolutionize the telegraph industry. Edison arrived in New York at one of the most exciting moments in the city's history. The completion of the Transcontinental Railroad had just connected the Atlantic and Pacific coasts, and New York was establishing itself as the financial and commercial capital of a rapidly expanding nation. Telegraph lines were proliferating at an incredible rate, connecting not just major cities but small towns and remote settlements across the continent. This explosive growth in telegraph infrastructure created enormous opportunities for inventors who could solve the technical problems that came with rapid expansion. Message volumes were increasing faster than companies could install new lines, creating bottlenecks and delays that cost businesses money. The existing technology was being pushed to its limits, and companies were desperate for innovations that could increase capacity without requiring massive new investments in infrastructure. Edison recognized that he had arrived at exactly the right moment. His years as a telegraph operator had given him intimate knowledge of the industry's problems, and his recent success with the stock ticker had proven his ability to create commercially viable solutions. What he needed now was access to the capital and business connections that only New York could provide. His timing couldn't have been better. Within days of his arrival, Edison found himself in the middle of one of the most dramatic episodes of his early career. The Golden Stock Telegraph Company, which operated the financial district's telegraph network, was experiencing a complete system failure during a period of frantic trading activity. Brokers throughout the city were cut off from current stock prices, and panic was beginning to spread through the financial markets. Edison happened to be in the company's offices when the crisis began, hoping to find employment as a telegraph operator. When the chief engineer confessed that he couldn't locate the source of the system failure, Edison asked permission to examine the equipment. Within minutes, he had identified the problem. A crucial spring in the central transmitter had broken, causing the entire network to malfunction. The repair took only a few minutes, but its impact on Edison's career was immense. The company's president, impressed by Edison's technical skills and quick thinking, immediately offered him a position as chief engineer. More importantly, the dramatic rescue of the telegraph system during a financial crisis established Edison's reputation as someone who could solve critical problems under pressure. This reputation would prove invaluable as Edison began developing the most important innovations of his early career. The telegraph industry was entering a period of intense competition, with companies racing to develop new technologies that could provide competitive advantages. Edison positioned himself at the center of this technological arms race, and the inventions that emerged from this period would establish him as one of America's premier inventors. Edison's position as chief engineer at Golden Stock Telegraph Company provided him with resources he had never before possessed: a fully equipped workshop, access to the latest materials and components, and most importantly, a steady income that allowed him to pursue his own inventions during his free time. The company's offices became his laboratory, and the city's financial district became his testing ground for revolutionary new technologies. His first major breakthrough came from a deceptively simple observation. Telegraph operators were constantly frustrated by the limitations of existing systems, which could only transmit one message at a time over each wire. During busy periods, urgent messages faced long delays as they waited in queue behind less important communications. Edison realized that if he could find a way to send multiple messages simultaneously over a single wire, he could multiply the capacity of existing telegraph networks without requiring companies to install expensive new infrastructure. Working through countless late nights in his makeshift laboratory, Edison developed what he called the quadruplex telegraph system. This revolutionary device could transmit 4 separate messages over a single wire simultaneously, 2 in each direction. The technical challenges were immense, requiring precise control of electrical currents and innovative switching mechanisms that could separate different signals without interference. The quadruplex system represented a quantum leap in telegraph efficiency, but Edison understood that technical achievement meant nothing without commercial success. He needed to prove that his invention could generate substantial profits for telegraph companies before anyone would invest in manufacturing and deploying it on a large scale. This meant not just building a working prototype, but demonstrating its reliability under real-world operating conditions. Edison's testing process revealed another crucial aspect of his approach to invention: his willingness to iterate endlessly until he achieved perfection. The first version of the quadruplex system worked in controlled laboratory conditions, but failed when subjected to the electrical interference and variable signal quality of actual telegraph networks. Rather than abandoning the project, Edison methodically identified each source of failure and redesigned the system to address every problem. This obsessive attention to detail required enormous patience and persistence. Edison often worked 18-hour days, testing circuit modifications, adjusting component specifications, and fine-tuning the system's performance. His assistants marveled at his ability to maintain focus through hundreds of failed experiments, all was convinced that the next iteration would solve the remaining problems. The breakthrough came when Edison realized that the key to reliable multi-message transmission lay not in more sophisticated electronics, but in more precise mechanical engineering. By developing new types of switches and relays that could operate with clockwork precision, he created a system that could maintain signal separation even under the harsh conditions of commercial telegraph operations. When the perfected quadruplex system was finally demonstrated to executives from Western Union, the results exceeded everyone's expectations. The device not only worked flawlessly, but actually improved signal quality compared to existing single-message systems. Company officials immediately recognized that Edison's invention could save them millions of dollars in infrastructure costs, while dramatically improving service to their customers. The financial negotiations surrounding the quadruplex telegraph marked Edison's first major business success. Western Union agreed to pay him $30,000 for the patent rights, an enormous sum for a 23-year-old inventor. More importantly, the company offered Edison a long-term consulting contract that would provide him with steady income while giving him access to their research facilities and technical expertise. This windfall allowed Edison to establish his first independent laboratory in Newark, New Jersey. Unlike his previous makeshift workshops, this facility was specifically designed for systematic invention and development. Edison equipped it with the finest available tools, instruments, and materials. He also hired a small team of skilled craftsmen and technicians who could help transform his ideas into working prototypes. The Newark laboratory represented a revolutionary approach to invention. Rather than working alone in isolation, Edison created what amounted to an invention factory where multiple projects could be pursued simultaneously by teams of specialists. This collaborative approach allowed him to tackle much more complex technical challenges while dramatically increasing his overall productivity. Edison's first major project in the new laboratory grew out of his continuing work on telegraph improvements. He had become convinced that the next breakthrough would come not from incremental improvements to existing systems, but from a completely different approach to long-distance communication. His target was the telephone, a revolutionary new technology that Alexander Graham Bell had recently demonstrated, but which remained too crude and unreliable for commercial use. Bell's telephone could transmit voice communications over short distances, but the sound quality was poor and the range was severely limited. Edison believed he could solve these problems by applying the same systematic approach that had made his quadruplex telegraph successful. He began by carefully analyzing every component of Bell's design, identifying the specific technical limitations that prevented clear, long-distance voice transmission. The breakthrough came when Edison focused on the telephone's transmitter, the component that converted sound waves into electrical signals. Bell's design used a relatively simple mechanism that produced weak, distorted signals that degraded rapidly over long distances. Edison realized that he needed to find a way to amplify and clarify these signals without introducing additional distortion. After months of experimentation with different materials and configurations, Edison discovered that carbon granules could serve as a variable resistance element that would strengthen telephone signals dramatically. When sound waves compressed the carbon granules, their electrical resistance changed proportionally, creating much stronger and clearer electrical signals that could travel much greater distances without degradation. Edison's carbon transmitter transformed the telephone from an interesting scientific curiosity into a practical communication tool. His design produced such clear sound quality over such impressive distances that it remained the standard for telephone systems for nearly a century. More importantly for Edison's career, the carbon transmitter established his reputation as an inventor who could not just create new technologies, but perfect existing ones to the point where they became commercially viable. The success of the carbon transmitter brought Edison to the attention of the most powerful business leaders in America. Railroad executives, mining company owners, and industrial magnates began seeking him out, hoping to commission inventions that could solve their specific technical challenges. Edison discovered that he could command enormous fees for custom invention work, but he also realized that this approach would limit his impact to solving individual problems, rather than creating technologies that could transform entire industries. This realization led Edison to make one of the most important decisions of his career. Rather than continuing to work as a consulting inventor for hire, he would establish a new type of research facility dedicated to systematic invention across multiple fields simultaneously. His goal was nothing less than to industrialize the process of invention itself, creating a steady stream of commercially viable innovations that could spawn entire new industries. In 1876, Edison purchased 14 acres of land in Menlo Park, New Jersey, and began construction of what he called his invention factory. The facility was unlike anything that had existed before, combining the resources of a university research laboratory with the practical focus of a commercial manufacturing operation. Edison's vision was to create a place where teams of inventors, craftsmen, and technicians could work together to solve the most challenging technical problems of the industrial age. The main laboratory building at Menlo Park was designed to accommodate multiple research projects simultaneously. Edison equipped it with every tool and instrument available, from precision measuring devices to heavy machinery for building large prototypes. He also established a comprehensive library of scientific and technical publications, ensuring that his team would have access to the latest discoveries and developments from around the world. But Edison's most important innovation at Menlo Park was not technological, but organizational. He recruited a diverse team of specialists who could contribute different types of expertise to invention projects. The team included mathematical theorists who could work out the principles behind new technologies, skilled craftsmen who could build precise mechanical components, and business-minded individuals who could evaluate the commercial potential of different inventions. This collaborative approach allowed Edison to pursue much more ambitious projects than any individual inventor could tackle alone. Instead of focusing on incremental improvements to existing technologies, the Menlo Park team could attempt to create entirely new types of devices that required breakthroughs in multiple technical areas simultaneously. Edison's first major success at Menlo Park came from an unexpected direction. While working on improvements to the telephone system, he discovered that he could record sound waves by using a needle to trace their patterns onto a rotating cylinder covered with tin foil. When he reversed the process, running the needle back over the traced patterns, the original sounds were reproduced with startling clarity. The phonograph, as Edison named his sound recording device, created an international sensation. For the first time in human history, sound could be captured, preserved, and reproduced at will. The implications were staggering. Music could be recorded and distributed, important speeches could be preserved for posterity, and messages could be sent in the speaker's own voice rather than written text. Demonstrations of the phonograph drew enormous crowds wherever Edison appeared. Newspapers around the world hailed him as the Wizard of Menlo Park, and scientific societies competed to honor him with awards and memberships. The phonograph established Edison's reputation as not just a skilled inventor, but as a genius capable of creating technologies that seemed almost magical to contemporary observers. But Edison's greatest triumph was still ahead of him, growing out of his systematic study of a problem that had frustrated inventors for decades: how to create a practical system for electric lighting that could compete economically with gas lamps and candles. The challenge of electric lighting had tantalized inventors and scientists for generations, but every previous attempt had failed to overcome fundamental technical and economic obstacles. Arc lighting systems existed but were blindingly bright, impossibly expensive, and suitable only for illuminating large outdoor spaces like city streets or factory yards. What the world needed was a form of electric lighting that could safely and affordably illuminate homes, offices, and shops with the gentle, controllable glow that people associated with gas lamps and oil lanterns. Edison understood that solving the lighting problem would require more than just inventing a better light bulb. He would need to create an entire electrical system that could generate, distribute, and control electric power safely and economically. This meant developing not just the light itself, but also the generators to produce electricity, the wiring systems to carry it, the meters to measure consumption, and the switches and fixtures to control it in individual buildings. The technical challenges were staggering. Electric current powerful enough to produce useful light was dangerous and difficult to control. Existing electrical generators were massive, expensive machines that could only be operated by skilled technicians. The copper wire needed for electrical distribution was costly, and no one had figured out how to wire buildings safely without creating fire hazards or electrocution risks. But Edison had learned from his telegraph work that the most difficult problems often yielded to systematic analysis and methodical experimentation. He began by studying every aspect of the existing gas lighting industry, from the economics of fuel production and distribution to the social patterns of how people actually used artificial light in their daily lives. This market research revealed crucial insights that would guide his technical development work. Gas companies had succeeded by creating complete systems that handled every aspect of lighting service. They produced gas in central facilities, distributed it through underground pipe networks, and provided customers with simple fixtures that could be operated safely by anyone. Customers paid monthly bills based on their actual consumption, making the service affordable even for middle-class families. Edison realized that electric lighting would only succeed if it could replicate this complete service model while offering significant advantages over gas. Electric light would need to be cleaner, safer, more convenient, and ultimately cheaper than gas lighting. This meant that his electrical system would have to be not just technically superior, but economically competitive with an established industry that had decades of experience optimizing costs and improving efficiency. Working with his Menlo Park team, Edison began tackling each component of the electrical lighting puzzle simultaneously. While some researchers focused on developing a practical incandescent bulb, others worked on generator design, electrical distribution networks, and safety systems. This parallel development approach allowed rapid progress across multiple technical fronts, while ensuring that all system components would work together seamlessly. The light bulb itself presented the most visible challenge, but in many ways it was the least difficult part of the overall system. Edison understood that the key to incandescent lighting lay in finding a material that could glow brightly when heated by electric current without burning up or melting. Previous inventors had experimented with various metals and carbon filaments, but none had achieved the combination of brightness, longevity, and cost-effectiveness needed for commercial success. Edison's approach to filament development exemplified his systematic methodology. Rather than relying on theoretical knowledge or random experimentation, he organized a comprehensive testing program that would evaluate thousands of different materials under controlled conditions. His team tested everything from human hair to exotic plant fibers, carefully documenting the performance characteristics of each potential filament material. The testing process was painstakingly thorough. Each filament candidate was subjected to identical electrical loads, while researchers measured brightness output, operating temperature, and lifespan. Materials that showed promise in initial tests were subjected to extended durability trials to determine how long they could operate before burning out. The most promising candidates were then tested under various environmental conditions to ensure reliable performance in real-world applications. This exhaustive testing revealed that carbonized organic materials offered the best combination of electrical properties, durability, and manufacturing feasibility. Edison's team eventually focused on bamboo fibers, which could be processed into extremely thin, uniform filaments that glowed brilliantly while lasting for hundreds of hours of operation. The bamboo filament bulbs produced warm, steady light that closely resembled the familiar glow of gas flames, making them psychologically acceptable to consumers accustomed to gas lighting. But developing a practical light bulb was only the beginning of Edison's electrical lighting challenge. The real breakthrough came with his revolutionary approach to electrical power distribution. Previous inventors had assumed that electric lighting systems would need to use high-voltage, direct current, similar to the powerful arc lighting systems already in use for street lighting. Edison realized that high-voltage systems were fundamentally unsuitable for residential and commercial applications. High voltages were dangerous, requiring extensive safety precautions and specialized equipment that would make installation and maintenance prohibitively expensive. More importantly, high-voltage systems could not easily provide the fine control over individual lights that customers expected from gas lighting systems. Instead, Edison designed his system around low-voltage direct current that could be safely handled by ordinary electricians and building maintenance workers. This approach required much more copper wire for distribution networks, increasing installation costs, but it enabled the creation of lighting systems that were genuinely safe and user-friendly. Individual lights could be controlled with simple switches, and electrical problems were unlikely to cause fires or injuries. The low-voltage approach also enabled Edison to create the parallel circuit design that became the foundation of all modern electrical systems. Instead of connecting lights in series like Christmas tree bulbs, where the failure of one bulb would extinguish the entire circuit, Edison's parallel circuits allowed each light to operate independently. Customers could turn individual lights on and off without affecting other lights in the building, and burned-out bulbs could be replaced without interrupting electrical service to other fixtures. Edison's power distribution system required the development of entirely new types of electrical generators, specifically designed for lighting applications. Existing generators were built for powering industrial machinery and produced electrical current with highly variable voltage and frequency characteristics that would cause incandescent bulbs to flicker and burn out prematurely. Working with his mechanical engineers, Edison designed a new type of steam-powered generator that could produce steady, reliable electrical current suitable for lighting applications. These generators incorporated sophisticated voltage regulation systems that automatically adjusted power output to maintain consistent electrical supply even as lighting loads varied throughout the day. The generator design process revealed Edison's growing understanding of the relationship between technical innovation and manufacturing economics. His generators needed to be not just technically superior, but also economical to manufacture and maintain. This meant designing systems that could be built using standard industrial components and maintained by mechanics with conventional training rather than specialized electrical expertise. Edison's complete electrical lighting system was first demonstrated to the public in December 1879, when he illuminated his entire Menlo Park laboratory complex using electricity generated on site. The demonstration drew enormous crowds of visitors, including newspaper reporters, potential investors, and representatives from gas lighting companies who wanted to evaluate this potential threat to their industry. The public response was overwhelmingly enthusiastic. Visitors marveled at the clean, bright light produced by Edison's bulbs and the convenient control provided by electrical switches. Unlike gas flames, electric lights produced no smoke, consumed no oxygen, and created no fire hazard. They could be turned on and off instantly, without the delay required to light gas fixtures, and their brightness could be controlled by using bulbs of different wattages. But Edison understood that public enthusiasm meant nothing without commercial viability. Gas lighting was a mature industry with established infrastructure and decades of experience controlling costs. Electric lighting would only succeed if it could offer comparable service at competitive prices while providing clear advantages that justified any additional expense. To prove the commercial feasibility of electric lighting, Edison decided to create a complete electrical utility system that would serve actual customers in a real urban environment. He chose Lower Manhattan as his test market, partly because of its high concentration of potential customers, and partly because the area's dense development would make electrical distribution networks economical to install and operate. The Pearl Street Station, Edison's first commercial power plant, began operation in September 1882. The facility housed 6 massive steam generators that could supply electricity to approximately 400 customers within a 1 square mile service area. Underground cables carried low-voltage direct current through a network of electrical mains that connected to individual buildings through basement service connections. The Pearl Street system represented the birth of the modern electrical utility industry. For the first time, customers could purchase electricity the same way they bought gas service, paying monthly bills based on their actual consumption as measured by Edison's newly invented electrical meters. The system provided reliable, convenient electrical service that was competitively priced with gas lighting while offering significant advantages in cleanliness, safety, and convenience. The success of the Pearl Street demonstration convinced investors and business leaders that electric lighting represented a massive commercial opportunity. Within months of the system's debut, Edison found himself inundated with requests from cities around the world wanting to install similar electrical systems. The demand for electrical equipment far exceeded the manufacturing capacity of Edison's existing facilities, forcing him to rapidly expand his operations to meet growing market requirements. But success brought new challenges that would test Edison's abilities as both inventor and business leader. The electrical industry was attracting competition from other inventors and entrepreneurs who recognized the enormous profit potential of electric power systems. Some competitors were developing alternative technologies that threatened to make Edison's direct current systems obsolete, while others were simply copying his innovations and selling competing equipment at lower prices. The most serious competitive threat came from alternating current electrical systems being developed by inventors like Nikola Tesla and George Westinghouse. AC systems could transmit electricity over much longer distances than Edison's DC systems, potentially allowing a single power plant to serve customers across an entire city rather than just a small neighborhood. This advantage could dramatically reduce the cost of electrical service while making it practical to electrify suburban and rural areas that were too sparsely populated to support local power plants. Edison initially dismissed alternating current as a dangerous and impractical technology, but as AC systems began gaining market acceptance, he realized that his business empire faced an existential threat. The battle between DC and AC electrical systems would become known as the War of the Currents, and it would reveal aspects of Edison's character that contradicted his public image as a benevolent inventor working for the betterment of humanity. The War of the Currents would expose a darker side of Edison's personality that few had witnessed during his years as the celebrated Wizard of Menlo Park. When faced with the genuine possibility that his electrical empire might crumble before a superior technology, Edison abandoned the methodical scientific approach that had made him famous and instead embraced a campaign of fear, misinformation, and public spectacle that would forever tarnish his reputation. Edison's initial response to the alternating current threat was rooted in legitimate technical concerns. AC systems did operate at much higher voltages than his DC networks, and high-voltage electricity was genuinely more dangerous than the low-voltage systems he had designed for residential use. Early AC installations had indeed caused several accidents, including some fatalities due to inadequate safety precautions and the electrical industry's general inexperience with high-voltage systems. But as Westinghouse began winning major contracts for AC power systems, Edison's criticism evolved from scientific skepticism into something far more sinister. He launched a systematic propaganda campaign designed to convince the public that alternating current was inherently lethal and that anyone who installed AC electrical systems was essentially inviting death into their homes and businesses. Edison's anti-AC campaign reached its most disturbing phase when he began conducting public demonstrations designed to prove the deadly nature of alternating current. Working with Harold Brown, an electrical engineer who shared his opposition to AC systems, Edison organized a series of gruesome exhibitions in which laboratory animals were killed using alternating current electricity. These demonstrations were presented as scientific experiments, but their real purpose was to create horrifying associations between AC power and violent death. The animal experiments escalated in both scale and brutality as Edison became increasingly desperate to discredit his competitors. The demonstrations progressed from killing cats and dogs to eventually electrocuting a circus elephant named Topsy, an event that was filmed and distributed to newspapers across the country. Edison claimed these experiments proved that AC electricity was too dangerous for public use, but critics pointed out that any form of electricity, including his own DC systems, could be lethal if improperly handled. Edison's most controversial contribution to the AC controversy came when he secretly provided technical assistance for the development of the electric chair, the execution device that New York State was developing as a supposedly humane alternative to hanging. Edison ensured that the electric chair used alternating current, hoping to create a permanent association in the public mind between AC electricity and death. When the electric chair was first used to execute William Kemmler in 1890, the procedure was botched, requiring multiple attempts and causing the condemned man to suffer horribly before finally dying. Rather than being deterred by this gruesome outcome, Edison promoted the event as proof that AC electricity was inherently suited for killing. He even suggested that execution by electrocution should be called getting Westinghoused after his primary competitor. The depth of Edison's involvement in the electric chair project remained hidden for years, but when the details eventually emerged, they revealed a side of his character that shocked even his closest associates. The man who had built his reputation on creating technologies that improved human life had secretly worked to develop a device whose sole purpose was to kill people, all in service of a business strategy designed to destroy his competitors. Despite Edison's propaganda campaign, the technical advantages of alternating current proved impossible to overcome through public relations alone. AC systems could transmit power over distances that made DC systems economically impossible, and this fundamental advantage became increasingly important as electrical demands spread beyond dense urban centres to suburban and rural areas. The decisive moment in the War of the Currents came when Westinghouse won the contract to provide electrical systems for the 1893 World's Columbian Exposition in Chicago. The exposition would showcase the latest technological achievements to millions of visitors from around the world, and the electrical system that illuminated the fair would be seen as the technology of the future. Edison submitted a bid for the exposition contract, but his DC system would have required multiple power plants scattered throughout the fairgrounds, making it both expensive and impractical for such a large installation. Westinghouse's AC system could illuminate the entire exposition from a single central power plant, offering both economic advantages and superior reliability. When the World's Fair opened, visitors were dazzled by the brilliant electrical illumination provided by Westinghouse's AC systems. The exposition demonstrated conclusively that alternating current was not only safe when properly installed, but also far superior to DC systems for large-scale electrical applications. Edison's claims about AC danger were thoroughly discredited, and his reputation as an objective scientist was permanently damaged. The commercial implications of the exposition were immediate and devastating for Edison's electrical business. Orders for DC equipment plummeted as customers demanded the superior performance and lower costs offered by AC systems. Within a few years, Edison's electrical companies were forced to abandon DC technology and adopt AC systems to remain competitive. The failure of his electrical empire marked a turning point in Edison's career and personality. The man who had always been able to solve technical problems through methodical experimentation and systematic development had encountered a challenge that could not be overcome through invention alone. For the first time in his professional life, Edison had been decisively defeated by superior technology developed by competitors. Edison's response to this defeat revealed the psychological toll that constant innovation and business pressure had taken on him. Rather than gracefully accepting that AC technology was superior and adapting his business accordingly, Edison became increasingly bitter and paranoid, convinced that his competitors had succeeded through dishonest means rather than technical merit. This bitterness extended to his treatment of former employees and associates who had contributed to his earlier successes. Nikola Tesla, the brilliant Serbian inventor who had worked briefly for Edison before joining Westinghouse, became a particular target of Edison's resentment. Edison publicly disparaged Tesla's contributions to electrical development and attempted to minimize his role in creating the AC systems that had defeated Edison's DC technology. The conflict with Tesla highlighted another troubling aspect of Edison's character: his reluctance to share credit for innovations that emerged from his laboratories. While Edison had built his reputation on collaborative invention at Menlo Park, he increasingly claimed sole credit for technologies that had actually been developed by teams of skilled engineers and technicians working under his direction. This pattern of behavior became more pronounced as Edison's business empire evolved from invention-focused research laboratories into large manufacturing and marketing organizations. The intimate collaborative atmosphere that had characterized the early days at Menlo Park was replaced by more conventional corporate hierarchies in which Edison served as the public face and primary decision-maker for enterprises employing hundreds of workers. Edison's role as a celebrity inventor also began to conflict with the realities of managing complex business operations. Public appearances, patent litigation, and corporate strategy consumed increasing amounts of his time, leaving less opportunity for the hands-on experimentation and development work that had originally made him famous. The transformation from inventor to industrialist was not entirely voluntary. Edison's success had created financial obligations and business relationships that required constant attention to maintain. Investors who had provided capital for his various enterprises expected regular returns on their investments, and customers who depended on Edison's products demanded continuous technical support and product improvements. These business pressures forced Edison to delegate increasing responsibility for actual invention work to subordinates, while he focused on higher-level strategic decisions. This change in role was psychologically difficult for someone whose entire identity had been built around personal involvement in every aspect of the invention process. Edison's response to these pressures was to become increasingly controlling and demanding in his management style. He insisted on personally approving every significant decision made by his various companies, and he frequently overruled the recommendations of subordinates who had more specialized knowledge of particular technical or business areas. This micromanagement approach created significant inefficiencies in Edison's business operations and contributed to the competitive disadvantages that allowed rivals like Westinghouse to gain market share in key industries. While Edison was spending time on minor operational details, his competitors were focusing on strategic innovations that could transform entire markets. The motion picture industry provided Edison with an opportunity to demonstrate that he could still create revolutionary new technologies even as his electrical empire was crumbling. Working with William Dixon, one of his most talented assistants, Edison developed the kinetoscope, a device that could record and display moving images with unprecedented clarity and realism. The kinetoscope represented another example of Edison's ability to identify emerging market opportunities and develop technologies that could create entirely new industries. Just as he had recognized the commercial potential of electric lighting before most other inventors, Edison understood that moving pictures could become a major form of entertainment if the technology could be made practical and affordable. Edison's approach to motion picture development followed the same systematic methodology that had made his earlier inventions successful. Rather than trying to create a complete system immediately, he focused on solving the fundamental technical challenges involved in capturing, storing, and displaying moving images. Each component of the system was developed and tested independently before being integrated into the complete device. The key breakthrough came when Edison realized that motion pictures were essentially a rapid sequence of still photographs displayed quickly enough to create the illusion of continuous movement. This insight led him to develop a camera system that could capture individual photographic frames at precise intervals, and a display mechanism that could project these frames in sequence to recreate the original motion. The kinetoscope created another international sensation when it was first demonstrated to the public. Audiences were amazed by the lifelike quality of the moving images and the wide range of subjects that could be recorded and displayed. Edison quickly established a series of kinetoscope parlors where customers could pay to watch short films, creating the foundation of the commercial motion picture industry. But once again, Edison's initial technical success was followed by competitive challenges that tested his ability to maintain market leadership in the face of superior innovations developed by rivals. Other inventors, building on the principles demonstrated by the kinetoscope, began developing projection systems that could display moving pictures to large audiences simultaneously rather than requiring individual viewing through Edison's peephole device. Edison was slow to recognize the commercial importance of projection technology, partly because he was reluctant to abandon the kinetoscope design that had already proven successful, and partly because he failed to understand how projection could transform motion pictures from a novelty entertainment into a major industry comparable to legitimate theatre. This strategic misjudgment allowed competitors like the Lumiere brothers in France to gain early advantages in projection technology that would eventually make kinetoscope parlors obsolete. By the time Edison recognized the importance of projection and developed his own competing systems, other companies had already established dominant positions in the rapidly growing market for theatrical motion picture equipment. The pattern was becoming familiar. Edison would create a revolutionary new technology that established an entirely new industry, but then lose market leadership to competitors who improved upon his innovations or developed superior alternative approaches. His role was increasingly that of a pioneer who opened new technological frontiers, but was unable to maintain control over the industries he had created. This recurring pattern reflected fundamental changes in the nature of technological innovation during the late 19th century. The era of individual inventor entrepreneurs working in small laboratories was giving way to large corporate research organizations that could marshal resources and expertise far beyond what any individual could command. Edison's Menlo Park laboratory had been revolutionary for its time, but by the 1890s, companies like General Electric and Westinghouse were operating research facilities that employed dozens of specialized engineers and scientists working on coordinated development programs. These organizations could pursue multiple technological approaches simultaneously and could afford to invest in long-term research projects that might not yield immediate commercial returns. Edison's response to this competitive evolution was to expand his own operations and attempt to create corporate research organizations that could compete with those being developed by his rivals. But this expansion required him to move even further away from hands-on invention work and toward executive management responsibilities that were poorly suited to his temperament and skills. The transition from inventor to corporate executive was never complete for Edison. Throughout his later career, he continued to involve himself in detailed technical decisions that would normally be delegated to subordinate engineers. This hands-on approach sometimes produced breakthrough innovations, but it also created bottlenecks and inefficiencies that hampered his company's ability to respond quickly to changing market conditions. Edison's later years were marked by a series of ambitious projects that demonstrated both his continuing inventive genius and his growing disconnection from commercial realities. His work on iron ore processing, battery development, and cement manufacturing showed that he remained capable of revolutionary thinking, but these projects also revealed his increasing tendency to pursue technical perfection at the expense of economic viability. The iron ore concentration project exemplified both Edison's strengths and weaknesses as a mature inventor. Recognizing that high-grade iron ore deposits were becoming depleted, Edison developed an innovative magnetic separation process that could extract iron from low-grade ores that had previously been considered worthless. The technology was technically brilliant and could have revolutionized the steel industry by dramatically expanding available ore supplies. But Edison's obsession with perfecting every detail of the ore processing system led him to spend years and enormous amounts of money on refinements that provided marginal improvements in efficiency. While he was pursuing technical perfection, competitors developed simpler and more economical approaches to ore processing that captured the commercial opportunities Edison had identified. The ore concentration failure was particularly painful because it represented Edison's attempt to establish himself as a major player in heavy industry rather than remaining confined to the electrical and entertainment technologies that had made him famous. The project's collapse cost him much of his personal fortune and forced him to abandon his dreams of industrial empire building. Edison's work on battery technology during the early 1900s showed that he retained his capacity for identifying important technological needs and developing innovative solutions. The growing automobile industry needed lightweight, reliable batteries that could provide electrical power for starting systems and accessories, and existing battery technologies were too heavy and unreliable for automotive applications. Working with characteristic persistence, Edison developed a new type of alkaline battery that offered significant advantages over existing lead-acid designs. His nickel-iron batteries were lighter, more durable, and less prone to failure than conventional alternatives, making them ideal for automotive and other demanding applications. But the battery project also revealed Edison's continuing difficulty in adapting to the realities of modern corporate competition. Rather than licensing his battery technology to established manufacturers who could quickly bring the product to market, Edison insisted on maintaining complete control over manufacturing and marketing. This decision delayed the commercial introduction of his batteries and allowed competitors to develop alternative technologies that captured much of the potential market. The pattern of technical brilliance, coupled with commercial misjudgment, characterized much of Edison's later career. His laboratories continued to produce innovative solutions to important technological problems, but his business strategies increasingly failed to capitalize effectively on these innovations. Part of the problem stemmed from Edison's reluctance to adapt his management style to the requirements of large-scale corporate operations. The collaborative, informal approach that had worked well at Menlo Park was poorly suited to organizations employing thousands of workers and serving national markets. But Edison found it difficult to delegate authority to professional managers who might have been better equipped to handle complex business operations. Edison's public persona during his later years became increasingly disconnected from his actual role in the technological developments attributed to him. Newspaper reporters and magazine writers continued to portray him as the hands-on inventor, personally responsible for every innovation emerging from his laboratories, when in reality, most of the detailed development work was being performed by teams of specialized engineers working under his general direction. This mythology served Edison's business interests by maintaining public confidence in his companies and their products, but it also created unrealistic expectations about his continuing ability to produce revolutionary innovations on demand. The pressure to maintain his reputation as America's premier inventor led Edison to make increasingly grandiose claims about future developments that his laboratories might produce. Some of these promises were fulfilled, but others proved to be premature or entirely unrealistic. Edison's predictions about the future of electric vehicles, for example, were based on his conviction that battery technology would advance more rapidly than internal combustion engines. When gasoline-powered automobiles proved more practical for most applications, Edison's electric vehicle ventures failed despite their technical merits. The gap between Edison's public image and his actual capabilities widened as he entered his 70s and 80s. Age inevitably reduced his energy and mental agility, but the public continued to expect the same revolutionary breakthroughs that had characterized his early career. This created pressure to maintain an impossibly high level of innovative output while dealing with the physical and mental limitations that come with advancing age. Edison's response to these pressures was to become increasingly reclusive and selective about his public appearances. He spent more time at his winter home in Fort Myers, Florida, where he could work on personal projects without the constant scrutiny that accompanied his activities in New Jersey. These Florida retreats provided opportunities for reflection and experimentation that were increasingly rare in his heavily scheduled business life. The Florida laboratory became Edison's refuge from the corporate responsibilities and public expectations that had come to dominate his career. Working with a small team of trusted associates, he could return to the hands-on experimentation and collaborative problem-solving that had originally made invention exciting for him. But even in this more relaxed environment, Edison continued to grapple with the fundamental challenge that had defined his entire career: how to balance his passion for pure invention with the commercial realities that determine whether his innovations would actually benefit humanity. The question of whether he had succeeded in this balance would ultimately define his legacy and influence how future generations would remember his contributions to technological progress. During his Florida years, Edison found solace in returning to the fundamental curiosity that had driven him since childhood. The warm climate and relaxed pace allowed him to pursue investigations that had nothing to do with commercial viability or market demands. He became fascinated with botanical research, particularly the possibility of finding domestic sources for rubber production that could reduce America's dependence on foreign suppliers. The rubber project exemplified Edison's continuing ability to identify problems of national importance and apply systematic investigation to find solutions. World War I had demonstrated America's vulnerability to supply disruptions of critical materials, and rubber was essential for everything from automobile tires to military equipment. Edison believed that the right combination of plant breeding and processing techniques could create a domestic rubber industry using Native American plants. Working with characteristic thoroughness, Edison tested over 17,000 different plant species in his search for viable rubber sources. He established experimental gardens at his Fort Myers laboratory and developed new methods for extracting and processing rubber from various botanical sources. The project consumed years of effort and demonstrated that his methodical approach to problem solving remained as rigorous as ever. The rubber research also revealed Edison's growing concern with America's technological independence and national security. His experiences during the war had convinced him that the country needed to develop domestic sources for all critical materials rather than relying on potentially unreliable foreign suppliers. This patriotic motivation added personal meaning to work that might otherwise have seemed like abstract scientific investigation. But the rubber project, like many of Edison's later endeavours, was ultimately overtaken by developments he could not control. The invention of synthetic rubber by chemical companies eliminated the need for botanical alternatives, making Edison's extensive research commercially irrelevant. Once again, his technical achievements were rendered obsolete by innovations developed through different approaches. The pattern of displacement by superior alternatives had become a recurring theme in Edison's later career, reflecting the increasingly rapid pace of technological change during the early 20th century. Industries that had taken decades to develop during Edison's youth were now being transformed within a few years by new discoveries and innovations. Edison's response to this acceleration was characteristically stubborn. Rather than accepting that the era of individual inventor entrepreneurs had passed, he continued to believe that personal genius and methodical experimentation could overcome any technical challenge. This conviction led him to pursue increasingly ambitious projects that required resources and expertise beyond what his laboratories could provide. The cement manufacturing venture represented perhaps the most dramatic example of Edison's refusal to accept the limitations imposed by changing industrial conditions. Convinced that he could revolutionize the construction industry through improved cement production methods, Edison invested enormous resources in developing new types of kilns and processing equipment that could produce superior concrete at lower costs. The technical aspects of the cement project were typically brilliant. Edison's rotary kilns were more efficient than existing designs, and his concrete formulations offered genuine improvements in strength and durability. He even developed plans for using concrete to construct entire houses that could be mass-produced at costs comparable to traditional wood frame construction. But the cement venture failed because Edison underestimated the conservative nature of the construction industry and the difficulty of changing established building practices. Contractors were reluctant to experiment with new materials and methods that might create liability issues or require expensive retraining of workers. The concrete house concept was technically sound, but commercially premature by several decades. The failure of the cement project marked another significant financial loss for Edison and further reduced his ability to fund future research and development activities. More importantly, it demonstrated that even his most carefully planned ventures could fail when they conflicted with entrenched industry practices and consumer preferences. These repeated commercial disappointments might have discouraged a less determined inventor, but Edison's response was to become even more focused on pure research rather than commercial development. His final years were characterized by investigations into fundamental scientific questions that had intrigued him throughout his career, but which he had never had time to explore thoroughly. Edison's late career research into the nature of consciousness and the possibility of communication with the deceased reflected his growing interest in questions that transcended purely technological concerns. These investigations were highly speculative and produced no practical results, but they demonstrated that his curiosity remained as wide-ranging as it had been in his youth. The consciousness research also revealed Edison's increasing preoccupation with his own mortality and legacy. As he entered his 80s, he became more reflective about the meaning and impact of his long career. He spent considerable time organizing his papers and records, apparently hoping to ensure that future historians would have access to accurate information about his contributions to technological development. This concern with historical accuracy reflected Edison's awareness that his public image had become increasingly mythologized over the decades. Popular accounts of his career often emphasized dramatic breakthroughs and individual genius, while ignoring the collaborative nature of most invention work and the crucial role played by business and marketing considerations in determining commercial success. Edison's efforts to set the record straight were complicated by his own tendency to embellish stories about his early career and to claim credit for innovations that had actually emerged from team efforts. The line between legitimate self-promotion and historical distortion had become blurred over the years, making it difficult even for Edison himself to distinguish between accurate memories and improved versions of events. The complexity of Edison's personality became more apparent as he aged and became less concerned with maintaining his public image. Associates noted that he could be both generous and vindictive, brilliant and stubborn, inspiring and impossible to work with, often within the same conversation. These contradictions reflected the enormous pressures that had shaped his character over decades of public scrutiny and commercial competition. Edison's relationship with his family during his later years revealed another dimension of the costs associated with his single-minded pursuit of innovation and business success. His first marriage had ended with his wife's early death, partly due to the stress and isolation created by his obsessive work habits. His second marriage was more successful, but still strained by his tendency to prioritize laboratory work over family responsibilities. His children struggled with the burden of being Edison's offspring, facing constant comparisons to their famous father and expectations that they would inherit his inventive abilities. Some followed careers in engineering and business, but none achieved the level of success that would have satisfied public expectations or their father's standards. The family dynamics reflected a broader pattern in Edison's personal relationships. His intense focus on technical and business challenges often left little emotional energy for maintaining close personal connections. Many of his early collaborators and friends gradually drifted away as his success created barriers to the informal relationships that had characterized his early career. Edison's increasing isolation was partly self-imposed as he became more selective about personal and professional associations. The bitter experiences of the War of the Currents had taught him to be suspicious of potential competitors and collaborators, leading him to maintain tighter control over his operations and to share less information about his current projects. This defensive approach may have protected Edison from some business risks, but it also limited his ability to benefit from the insights and expertise of others. The collaborative spirit that had made Menlo Park so productive was gradually replaced by a more hierarchical and secretive organizational culture that discouraged the free exchange of ideas. The transformation of Edison's laboratories from creative workshops into conventional corporate research facilities reflected broader changes in American industry during the early 20th century. The era of individual inventor entrepreneurs was giving way to large corporate organizations that could marshal resources and expertise far beyond what any individual could command. Edison's response to this industrial evolution was ambivalent. He recognized the advantages offered by large-scale research organizations, but was reluctant to surrender the personal control that had always been central to his approach to invention and business. This tension between efficiency and autonomy would characterize his final decades and influence his decisions about the future of his various enterprises. The question of succession became increasingly important as Edison aged and his energy declined. None of his children showed the combination of technical ability and business acumen that would have made them obvious heirs to his industrial empire. Professional managers could handle day-to-day operations, but they lacked the innovative vision that had created the companies in the first place. Edison's reluctance to delegate fundamental decision-making authority created a leadership vacuum that became more problematic as his companies faced increasingly sophisticated competition. While he remained nominally in charge, the reality was that many important strategic decisions were being postponed or made by default rather than through conscious choice. This leadership crisis was exacerbated by Edison's continuing involvement in multiple, often unrelated, business ventures. His attention was divided between electric power systems, motion picture equipment, battery manufacturing, cement production, and various research projects, making it impossible for him to provide effective direction to any single enterprise. The diversification that had once been a source of strength became a liability as each industry developed its own specialized requirements and competitive dynamics. Edison's broad knowledge and experience were less valuable than deep expertise in particular technical or market areas, but his management style made it difficult to delegate authority to specialists who might have been better equipped to handle specific challenges. The motion picture industry provided a particularly clear example of how Edison's management approach had become unsuited to modern competitive conditions. While his early kinetoscope had established the technical foundation for the entire industry, his companies had lost market leadership to more agile competitors who could respond more quickly to changing consumer preferences and technological developments. Edison's attempts to maintain control over motion picture technology through patent litigation were ultimately unsuccessful and consumed resources that might have been better invested in product development and marketing. The legal battles created adversarial relationships with other industry participants and contributed to an atmosphere of suspicion and conflict that hindered collaborative development efforts. The patent strategy that had served Edison well during his early career became increasingly problematic as the pace of technological change accelerated and the number of competing inventors multiplied. Legal protection for individual innovations became less valuable when entire technologies could be made obsolete within a few years by fundamentally different approaches. Edison's continuing reliance on patent litigation as a competitive strategy reflected his difficulty in adapting to changed industrial conditions that favored rapid product development and market responsiveness over legal protection of existing technologies. This strategic inflexibility would characterize many of his later business decisions and contribute to the gradual decline of his commercial influence. Despite these business challenges, Edison's reputation as America's premier inventor remained largely intact throughout his later years. The public continued to associate his name with technological progress and innovation, and his opinions on scientific and technical matters were sought by journalists and government officials dealing with various national challenges. This continuing public prominence provided Edison with opportunities to influence national policy on issues related to technological development and industrial competitiveness. His advocacy for increased investment in scientific research and technical education helped shape government programs that would benefit future generations of American inventors and engineers. Edison's role as a public spokesman for technological progress also allowed him to promote his vision of how invention and innovation could contribute to social improvement and economic development. His optimistic belief in technology's potential to solve human problems remained undimmed despite his personal experiences with commercial disappointment and competitive failure. The contrast between Edison's public optimism and his private struggles with business and personal challenges reflected the complex relationship between his identity as a celebrated inventor and his reality as an aging entrepreneur dealing with declining influence and energy. This tension would define his final years and influence how he approached the question of his own legacy and historical significance. As the 1920s progressed, Edison's direct involvement in day-to-day business operations continued to diminish, but his symbolic importance as America's greatest inventor remained as strong as ever. The challenge he faced was how to manage this transition from active participant to historical figure, while maintaining some measure of control over how his contributions would be remembered and evaluated by future generations. The decade of the 1920s brought both recognition and reflection as Edison approached his final years. The man who had once worked 18-hour days with boundless energy now found himself moving more slowly through the familiar halls of his West Orange laboratory. His hearing, which had been problematic since youth, had deteriorated significantly, forcing him to rely increasingly on written communication with his staff and visitors. Yet his mind remained sharp, and his curiosity about the natural world continued to drive new investigations. The American public's fascination with Edison showed no signs of waning. Newspapers regularly reported on his activities, however mundane, and his birthday celebrations became national events. Radio stations broadcast interviews with the aging inventor, though his hearing difficulties made these sessions challenging for both Edison and his interviewers. The irony was not lost on observers that the man who had contributed so much to communication technology struggled to participate in the medium that was transforming American culture. Edison's relationship with the rapidly evolving technological landscape of the 1920s was complex and sometimes contradictory. He watched with interest as radio broadcasting exploded across the nation, recognizing that his early work on wireless transmission had contributed to this revolution. Yet he also expressed skepticism about some of the social implications of mass communication, worrying that radio might make people more passive consumers of entertainment rather than active participants in their communities. The automobile industry's transformation from luxury novelty to mass transportation fascinated Edison, particularly given his early involvement in electric vehicle development. Henry Ford had become a close personal friend, and their annual camping trips with other prominent Americans became legendary examples of how successful entrepreneurs could maintain friendships despite fierce business competition. These expeditions provided Edison with opportunities to observe Ford's mass production methods firsthand and to reflect on how different approaches to manufacturing could transform entire industries. Ford's success with gasoline-powered vehicles had definitively settled the question of automotive propulsion that had occupied Edison for years. While his electric vehicles had possessed technical advantages in reliability and ease of operation, the limitations of battery technology had made them unsuitable for the long-distance travel that Americans increasingly demanded. Edison gracefully acknowledged that Ford's approach had proven superior for most applications, though he continued to believe that electric vehicles might find specialized roles in urban transportation. The friendship with Ford also highlighted Edison's evolving perspective on business success and technological progress. Where Edison had always focused on individual innovation and personal control over his enterprises, Ford had demonstrated the power of systematic organization and standardized production methods. The contrast between their approaches reflected broader changes in American industry that had occurred during Edison's lifetime. Edison's observations about industrial evolution were shaped by his unique position as both participant and witness to America's transformation From an agricultural society to an industrial powerhouse, he had lived through the entire development cycle of multiple technologies, from their initial invention through commercial maturity to eventual obsolescence. This perspective gave him insights into the patterns and rhythms of technological change that few other individuals could match. The rubber research project that occupied much of Edison's attention during the 1920s reflected both his continuing faith in systematic investigation and his growing awareness of America's vulnerability in an increasingly interconnected world. The Great War had demonstrated how international conflicts could disrupt supply chains for critical materials, and Edison believed that domestic alternatives needed to be developed for strategic reasons as well as economic ones. Working with characteristic persistence, Edison established extensive experimental gardens where he tested thousands of plant varieties for their rubber-producing potential. The project required him to master botanical sciences that had played little role in his earlier electrical and mechanical inventions. This intellectual challenge energized him and demonstrated that his capacity for learning new fields remained intact despite his advanced age. The rubber investigation also provided Edison with opportunities to collaborate with agricultural researchers and botanists who brought different perspectives to problem solving than the engineers and technicians who had dominated his earlier projects. These interdisciplinary collaborations enriched his understanding of how scientific knowledge could be applied to practical problems and reinforced his belief that innovation required contributions from multiple fields of expertise. Edison's approach to the rubber project exemplified his lifelong commitment to thorough investigation and systematic testing. Rather than relying on theoretical knowledge or accepting conventional wisdom about which plants might produce useful rubber, he insisted on practical experimentation with actual specimens grown under controlled conditions. This empirical approach generated enormous amounts of data that needed to be carefully analysed to identify the most promising candidates for further development. The methodical nature of the rubber research appealed to Edison's engineering mindset, but it also reflected his growing interest in understanding fundamental principles rather than simply developing commercially viable products. The project represented a return to pure research that reminded him of his earliest days as an inventor, when curiosity and discovery had been more important than immediate profitability. As the rubber project progressed, Edison became increasingly absorbed in the biological and chemical processes that determined how different plants produced and stored rubber compounds. This scientific investigation required him to study cellular structures, metabolic pathways, and genetic factors that influenced rubber production. The complexity of these biological systems challenged his mechanical engineering background and forced him to develop new approaches to analysis and experimentation. The interdisciplinary nature of the rubber research brought Edison into contact with university scientists and government researchers who were pursuing similar investigations for both commercial and strategic reasons. These collaborations exposed him to academic research methods that differed significantly from the commercially driven approaches that had characterized his industrial laboratories. Edison's interactions with academic researchers revealed both the strengths and limitations of his practical approach to invention. While his emphasis on systematic testing and real-world applications impressed university scientists, some questioned whether his methods were sophisticated enough to address the complex theoretical questions underlying rubber production in plants. These methodological differences reflected broader tensions between academic and industrial research that were becoming more pronounced as scientific investigation became increasingly specialized and theoretical. Edison represented an older tradition of practical invention that emphasized empirical testing and commercial application, while the academic researchers favored theoretical analysis and fundamental understanding of underlying principles. Despite these philosophical differences, Edison's rubber project produced valuable results that contributed to the broader scientific understanding of plant-based rubber production. His systematic testing of thousands of plant species generated a comprehensive database of information that proved useful for other researchers working on similar problems. The practical applications of Edison's rubber research were ultimately limited by developments in synthetic chemistry that provided alternative sources of rubber production. Chemical companies had learned to manufacture artificial rubber using petroleum-based feedstocks, eliminating the need for plant-based alternatives except in specialized applications. This outcome disappointed Edison, who had hoped that his botanical research would create new agricultural industries that could provide rural communities with additional sources of income while reducing America's dependence on foreign rubber suppliers. The displacement of his natural rubber alternatives by synthetic production methods represented another example of how rapidly evolving technology could make even the most careful research obsolete. Edison's response to the commercial failure of his rubber project was characteristically philosophical. Rather than viewing the years of investigation as wasted effort, he emphasized the scientific knowledge that had been gained and the potential applications that might emerge in the future. This perspective reflected his lifelong belief that genuine research always produced valuable results, even when those results differed from original expectations. The rubber project's conclusion coincided with Edison's growing awareness that his active research career was drawing to a close. At 83 years old, he lacked the physical stamina for the intensive laboratory work that had always been central to his approach to invention. The daily routines of experimentation and testing that had sustained him throughout his career were becoming increasingly difficult to maintain. Edison's adaptation to reduced physical capabilities revealed both his resilience and his continuing commitment to technological investigation. Unable to spend long hours in the laboratory, he focused more attention on analyzing data, reviewing research reports, and consulting with younger investigators who could carry out the detailed, experimental work that he could no longer perform himself. This transition from hands-on experimenter to senior advisor was emotionally challenging for someone whose identity had always been tied to personal involvement in every aspect of the invention process. Edison struggled with the reality that his most productive years as an active inventor were behind him, even as his reputation and influence remained as strong as ever. The shift from active research to advisory roles also provided Edison with opportunities to reflect on the broader patterns and meanings of his long career. He spent increasing amounts of time organizing his papers, recording his recollections of important events, and thinking about how his experiences might provide guidance for future generations of inventors and entrepreneurs. These reflective activities brought Edison into contact with historians, biographers, and journalists who were beginning to document the story of American technological development during the late 19th and early 20th centuries. Their questions forced him to think systematically about which aspects of his career had been most significant and what lessons might be drawn from both his successes and failures. Edison's conversations with historians revealed his continuing ambivalence about how his contributions should be evaluated and remembered. He took pride in the practical innovations that had improved people's daily lives, but he also worried that his business activities and competitive strategies might overshadow his genuine scientific achievements. The complexity of Edison's legacy reflected the inherent tensions between invention and commercialization that had shaped his entire career. His greatest successes had always required both technical brilliance and business acumen, but these different aspects of innovation sometimes conflicted with each other in ways that complicated simple assessments of his historical significance. As Edison entered the final phase of his life, he remained optimistic about America's technological future, despite his personal experiences with competitive disappointment and commercial failure. His faith in the power of systematic investigation and practical application to solve human problems had been tested but not broken by decades of both triumph and setback. The approaching end of Edison's career coincided with the beginning of a new era in American science and technology. The research universities, government laboratories, and corporate research facilities that would dominate 20th century innovation were taking shape, building on foundations that Edison and his contemporaries had established, but extending far beyond what any individual inventor could accomplish. Edison's awareness of these institutional changes influenced his thinking about how future technological development might proceed. He recognized that the era of individual inventor entrepreneurs was giving way to more collaborative and systematic approaches to research and development, but he remained convinced that personal creativity and determination would continue to play crucial roles in genuine innovation. The question of how individual genius would interact with institutional resources in future technological development occupied much of Edison's attention during his final years. He had witnessed the transformation of invention from a largely individual activity to an increasingly collaborative enterprise, and he understood that this evolution would continue long after his own career had ended. Edison's perspective on these changes was shaped by his unique position as both creator and witness to many of the institutional innovations that were reshaping American technology. His establishment of the Menlo Park Laboratory had demonstrated the potential of organized research, while his later experiences with large corporate organizations had revealed both the opportunities and limitations of institutional approaches to invention. The balance between individual creativity and organizational efficiency remained a central concern for Edison as he considered how his own legacy might influence future generations of inventors. He wanted to ensure that the systematic methods he had developed would continue to be used effectively, while also preserving space for the kind of individual initiative and creative risk-taking that had made his own career possible. These considerations about the future of American innovation reflected Edison's deep concern for his country's technological competitiveness and industrial strength. The Great War had demonstrated the crucial importance of technological superiority in international competition, and Edison believed that America's continued prosperity depended on maintaining leadership in scientific research and practical innovation. Edison's patriotic motivations had always influenced his choice of research projects and business strategies, but they became even more prominent during his final years as he reflected on his contributions to American industrial development. He took pride in having helped establish the technological foundations that had made America a dominant force in global commerce and manufacturing. The intersection of personal legacy and national interest shaped many of Edison's decisions about how to spend his remaining time and energy. Rather than focusing solely on projects that might enhance his reputation or provide financial returns, he increasingly chose activities that he believed would benefit future generations of American inventors and entrepreneurs. This shift toward legacy-building activities reflected Edison's growing awareness that his time was limited and that his influence would ultimately depend on the institutions, methods, and examples he left behind, rather than on any additional inventions he might create. The question was no longer what he could accomplish personally, but how his lifetime of experience could best serve the cause of continued technological progress. Edison's final years were marked by a profound shift in how he viewed his role in the rapidly changing technological landscape of America. The man who had once driven himself relentlessly through 18-hour workdays now found himself moving through a different rhythm, one dictated not by the urgent demands of invention deadlines, but by the deeper currents of reflection and legacy. His laboratory at West Orange had become less a factory of innovation and more a shrine to decades of methodical investigation, where younger engineers carried forward the systematic approaches he had perfected, while Edison himself served as the living embodiment of American ingenuity. The physical decline that accompanied his advancing age was undeniable, yet somehow seemed secondary to the intellectual vigor that continued to animate his conversations and correspondence. Visitors to the laboratory often remarked on the contrast between Edison's frail appearance and the sharp intensity that still flickered in his eyes when discussing technical problems or future possibilities. His deafness, which had been a constant companion since youth, now served almost as a filter that allowed him to focus entirely on the ideas and concepts that truly mattered to him, shutting out the trivial distractions that might have dissipated his remaining energy. The America of the late 1920s bore little resemblance to the nation Edison had known in his youth. The rural agricultural society that had shaped his early experiences had been transformed into an urban industrial powerhouse that relied on technologies he had helped create, but which had evolved far beyond his original conceptions. Electric lights illuminated every city street and home. Motion pictures had become a massive entertainment industry, and recorded music filled the air through radio broadcasts that reached into the most remote corners of the continent. Yet Edison's relationship with this transformed world remained complex and sometimes conflicted. While he took satisfaction in knowing that his innovations had contributed to American prosperity and convenience, he also worried about some of the social consequences of technological progress. The passive consumption of entertainment through radio and movies troubled him, as did the increasing standardization and mechanization of work that seemed to leave little room for individual creativity and initiative. These concerns reflected Edison's lifelong belief that technology should enhance human capabilities rather than replace them, that innovation should empower individuals to accomplish more rather than making them dependent on systems they could not understand or control. His own approach to invention had always emphasized understanding the fundamental principles behind every device he created, and he feared that future generations might become so dependent on complex technologies that they would lose the ability to think independently about technical problems. The irony was not lost on Edison that his own innovations had contributed to this trend toward technological dependence. The electrical power systems he had developed were so complex and interconnected that ordinary users had no choice but to accept them as mysterious services provided by distant corporations. The motion picture industry had evolved into a form of mass entertainment that encouraged audiences to become passive consumers rather than active participants in creative activities. Edison's response to these concerns was to emphasize the importance of scientific education and technical literacy in preparing Americans for an increasingly technological future. He believed that every citizen needed to understand at least the basic principles behind the technologies that shaped their daily lives, and he advocated for educational reforms that would make scientific thinking and practical problem-solving central elements of American schooling. This educational mission became one of Edison's primary preoccupations during his final years. He worked with educators and government officials to develop curricula that would teach students not just scientific facts, but also the methodical approaches to investigation and experimentation that had made his own career possible. The goal was to create a generation of Americans who could think creatively about technical challenges rather than simply accepting whatever solutions were provided by experts. The scope of Edison's educational vision reflected his understanding that technological innovation required more than just individual genius or even well-equipped laboratories. It demanded a cultural commitment to systematic investigation, practical experimentation, and the application of scientific knowledge to real-world problems. These attitudes and methods needed to be widely distributed throughout American society if the nation was to maintain its technological leadership in an increasingly competitive world. Thomas Edison died peacefully in his sleep on October 18, 1931, at his Glenmont estate in West Orange, New Jersey. He was 84 years old and had spent virtually every day of those 8 decades consumed by the irrepressible urge to understand, improve, and invent. His final words, spoken to his wife Mina, were reportedly, "It is very beautiful over there," suggesting that, even in death, Edison remained the eternal explorer, curious about what lay beyond the next horizon. When the news of Edison's death reached the world, the response was unprecedented. President Herbert Hoover suggested that all of America's electrical power should be shut off simultaneously as a tribute to the man who had illuminated the modern world. The idea proved impractical. The nation was now too dependent on electricity to function without it, even briefly. But the gesture captured the profound recognition that Edison had fundamentally transformed human civilization. The complexity of Edison's legacy mirrors the complexity of the man himself. He was simultaneously a brilliant inventor and a ruthless businessman, a methodical scientist and a shameless self-promoter, a collaborative leader and an egotistical competitor. His contributions to human progress are undeniable, from the light bulb that banished darkness, to the phonograph that captured sound, to the motion picture camera that preserved movement for eternity. Yet his methods were often questionable, his treatment of competitors sometimes brutal, and his later years marked by commercial failures and technological obsolescence. Perhaps the most honest assessment of Edison's life recognizes that he embodied both the greatest strengths and the most troubling contradictions of American industrial capitalism. His relentless drive to innovate and commercialize created technologies that genuinely improved millions of lives, but his equally relentless pursuit of market dominance sometimes led him to embrace tactics that contradicted his public image as a benevolent wizard working for humanity's benefit. What remains indisputable is that Edison changed the world in ways that continue to shape our daily existence more than a century after his death. Every time you flip a light switch, watch a movie, listen to recorded music, or use any of the countless electrical devices that surround us, you are experiencing the continued influence of Thomas Alva Edison. He didn't just invent the modern world, he taught us how to think about invention itself as a systematic, collaborative, and commercially viable enterprise. The boy who was once dismissed as addled by his schoolteacher ultimately proved that formal education means far less than curiosity, persistence, and the courage to question everything. Edison's true legacy lies not in any single invention, but in the revolutionary idea that human ingenuity, properly organized and relentlessly applied, can solve any problem and illuminate any darkness. In a world still grappling with technological challenges that would have seemed like magic to Edison's generation, that lesson remains as relevant as ever.